Hello everyone. In the last lecture, we had seen what is electromagnetic methods. Today, we are going to do the survey at IIT Madras thanks to our friends from Central Groundwater Board who were kind enough to organize this demonstration. Right. Anyhow, I would like to also give you a brief overview of the method we had seen. So, electromagnetic methods are usually also called as transient electromagnetic methods. That is what we are going to do. This is going to be carried out today with this instrument which is shown here. What we are planning to do today is we are going to do a size of 20 by 20 meter loop, right. That means a wire will be wound like this, right. The other two ends will be connected to the instrument. The size we are planning to do is 20 by 20 meters. So, the size corresponds to the depth of investigation, right. And we are going to follow coincident loop. That means transmitter and receiver both will be of 20 by 20 meters. Let us say this is the transmitter coil, then the receiver coil also will be kept like this. Okay. So, this is the receiver coil. Right. Both are going to be arranged like this, and we are going to apply time variant current to the transmitter. When you apply time variant current, so this, let us imagine this is the surface, imagine this is the transmitter coil. When the current is applied, electromagnetic field is created. The electromagnetic field in turn create eddy current in the earth. The amount of eddy current generated is received by the receiver coil, right. So, this is what we are going to do today in the field, and the secondary electromagnetic field that is going to be created is going to be received by the receiver coil. Okay, the receiver coil is going to be placed. So, here you can see a red wire, red is the transmitter and the blue cable is going to be used as a receiver. So, when we say coil, the coil is nothing but a simple wire, right, a copper wire, insulated copper wire, right, and the quantity of voltage which we measure in the receiver coil is the function of time after switching off the primary field. That means what we do here in transient electromagnetic is we will transmit current which will create electromagnetic field, then immediately we will switch off the application of current, then the remnant magnetic field would have created eddy current. That is what we are going to measure, right. And in order to also go for inversion to understand about the subsurface, in order to construct the image of subsurface, we are going to do minimum of 3 soundings are necessary. Hence, this is the transmitter coil. Right. Transmitter coil is going to be kept like this, which is 20 by 20 meter, and the receiver coil is going to be also kept like this, right. And we are going to keep moving the receiver coil by every 5 meters, right. Then this will be, let us say, first 0, the next one will be something like this. Let us say this is 5 meters and again next 5 meters, okay, 10 meters. That is what I have mentioned here, right. So, 3 soundings were carried out along a profile by moving only the receiver coil. This is the receiver, this is number 1, this is the transmitter. We do not move the transmitter coil, but the receiver is moved initially almost overlapped or half a meter or 1 meter, then we moved it by 1, 5, then 10 meters, right. Data was collected repeatedly, right. That means you can set the instrument to collect the data 4 times or 18 times or 16 times, right? Why? This is mainly to improve the results or to reduce the error, right? That means we had set the instrument to collect the data 16 times, right? That means 16 times the region will be energized, electromagnetic field will be created, switched off, then we will receive the voltage, right? The eddy current that got developed will be measured, right? Then we are going to use the data for inversion, right? That means we will invert the data and come out with the subsurface model. That is what we are planning to do today. And this is the instrument which is now ready for operation, right? And we are going to connect, as I told you, 2 cables. Here you can see a cable is connected, right? In order to pass the current, we use a battery. Here you can see the red color one is the battery, which is going to transmit the current, and you can see a red cable, which is going to be of 20 meter by 20 meter, right? So that means the same cable is wound in the form of a square. The size of that was, we kept it as 20 by 20 by 20 meters, right? All the 4 sides are of 20 meters. How does the size relate to the depth of penetration? If the size of the square is increased, more depth of investigation is possible, right? As of now, at least 3 times of that can be investigated. Our colleagues from Central Groundwater Board are now connecting. They are also assisted by our students from IIT Madras, right? We are just now connecting all the cables. That means 2 cables. One is the receiver, one is the transmitter. So for convenience, we are using the red color cable as indicating the red color cable is used as a transmitter, and the blue cable is going to be used as a receiver, right? Now you can see the instrument. The instrument is capable of taking measurement repeatedly, even up to 64 times. Only thing is, it requires some additional time, right? We need to spend additional time in the field, because every measurement will take about few seconds, not more than a minute, right? Suppose if you set the instrument to make measurement 64 times, it may take few minutes to complete one measurement, right? So as I told you, what we are going to do today is, we are going to carry out soundings 3 times. That means we are going to follow the coincident loop. That means both transmitter as well as the receiver are going to be in the form of a square, but the receiver's coil is going to be shifted 5 meters every time, so that we will have soundings at 3 locations, which is a minimum requirement to carry out inverse modeling, right? Now the system is ready, and the coil has been already kept at in the form of a square, right? Now we are going to make the measurement. We are going to commence the measurement. So now we have commenced our measurements. The instrument now transmits current using the battery in the transmitter coil. Then the applied current is stopped. Then the measurement is taken. Measurement of the electromagnetic impact of the electromagnetic. So you can see the rectangle. Now after completing one measurement, we are shifting the receiver coil by 5 meters from the previous location. So we are going to we are now arranging the cable for commencing the next measurement. So you can see the difference between the location of the transmitter and the receiver coil. Now we are commencing the second sound measurement using the second location, right? The sounding is being now made to take the next reading, next set of reading. After completing this, now we are going to shift the location of the receiver by another 5 meters. After doing this, we are now commencing the next measurement. Simultaneously, you can look at the display. It is able to carry out the inversion and gives us the subsurface model of the terrain over this site, right. After completing the survey, now the data has been stored in the system, right. After that, now the data can be used to come out with either as 1D sounding data, or we can also integrate the 3 soundings which we have made to come out with the inverse model. So, what is inverse model? We have been discussing about this in various at various times, right. So, in inversion, what we do is we assume certain subsurface configuration, right, and for the assumed subsurface geological condition, what is the signal which we are likely to get at the surface, right. This is derived by theoretical computations. Am I clear? Right. That means we will derive the theoretically expected results for the assumed subsurface layers. Let us say 1, 2, 3, they are of certain geological characteristics. For this assumed layer, when you do survey by 20 by 20 meter coincident loop, what is the signal which we will get can be theoretically computed. After arriving the theoretically computed results, we will compare the theoretical results with what was observed in the field, right. So, before looking into that, first let us see what we are going to get for the assumed is kept like this, and then we have a receiver which is also kept parallel. So, this is, let us say this is transmitter, this is receiver coil. Okay. Now, we have made one sounding. We had seen the video of we carrying out the survey, right. For this, we can arrive at a curve based on the time, right, we did at all these times, right. That means 1, 2, 3, 4, 5, 6, I think we have used 24. We made 24 soundings, right. And at different times, what was the apparent resistivity which we could get, which are plotted here. So, you can see a plot of time versus the resistivity that we have measured, right. How did we get this? We have generated a electromagnetic field using a transmitter coil. This electromagnetic field in turn resulted in eddy currents. Eddy currents are the currents that are generated within the subsurface due to the generation of electromagnetic field. The current which got developed is sensed by the receiver coil, which are plotted as time versus apparent resistivity. Then, as I was telling you just now, we come out with what is known as inverse model, right. To arrive at inverse modeling, what we do is, beneath the subsurface, we assume certain configuration, and then for the assumed configuration, when you do electromagnetic survey by 20 meter by 20 meter receiver and coil, what is the signal which we are expected to get is theoretically computed. Okay. So, on one hand, we determine the theoretically estimated, what we are going to do is, we are going to determine what is the signal that is going to get generated for the assumed geological conditions, right. So, based on theoretical consideration, we arrive at this curve, right. That means the system or the software will automatically assume certain subsurface conditions of different resistivities R1, R2, R3 and so on. For this, when you do survey at the surface by 20 meter by 20 meter coil, both transmitter and receiver, what is the expected signal can be theoretically determined. Then the computer will compare the theoretically derived data with the observed data, right. Then when there is a reasonably good match, we can also set, right. We can say a match of 90% I need, a 90% accuracy I need, or 95% accuracy I need. Accordingly, the system will take more time and then it will try to converge. That means every time it will have a theoretically derived data, it will compare with the field data. This is the field data. So, it will make several trial and error and then it will come out with the inverse model. Based on the inverse model, it is able to give us the values of the true resistivities of the layers that are present below the surface and their corresponding thicknesses. Is it clear? That means what we are doing is, we are doing inverse modeling work. In inverse modeling work, we don't use the field data, we use only some theoretical considerations. We assume different formations of different resistivities beneath the surface, then we derive the expected data. For, in this case, we have used 20 by 20 meter coincident loop arrangement, right. Then whatever estimated by inversion will be compared with the field data. So, this is field. On the other hand, we have a theoretically determined data. This is done by the software. Software, what it assumes? Software assumes some subsurface conditions for which it derives the theoretical curve. Both theoretical and field data are compared, and if there is good match, the model work will get over. If not, it does again. It changes the R values, then tries once again. Like that, it may try 100 times, 1000 times, because we are going to give the criteria. Do this trial and error until I get 95% match, right. Then the system stops and gives, what does it indicate? When there is a 95% match, whatever we have assumed is likely to exist at the site where we carried out the investigation. So, this is in simple terms about inversion, right. So, after that, the system gives us the thicknesses. This is the computer derived subsurface variation in the true resistivity, and this is the depth, right. So, that means now we have layer 1, 2, 3 and 4. The system considered the presence of 4 layers. Of our 4th layer, we do not know the thickness because it is likely to be infinite, right. So, up to 3 layers we are able to get the thicknesses. The first layer is about half a meter, second layer is of about 3 meters, third one is of about 20 meters, right. So, this is how for the first sounding we could get. That means this is the first sounding, that means this is the transmitter, this is the transmitter coil and this is the receiver coil. Okay. Then what did we do? We moved the separation distance between the transmitter and receiver was moved by 5 meters, right. So, this is what we have seen on the previous slide. After that, we moved it to 5 meters and then 10 meters. In the same way as I explained, for the remaining soundings also inversion was done and the corresponding thicknesses were estimated. This is at 0, 5 meters, 10 meters, right. So, 0 is like this. So, this is, let us say, transmitter, receiver was kept like this. So, this is transmitter, receiver, location 1. Then location 2, as I had drawn previously, it is shifted by 5 meters. The distance between these two is 5 meters. Again, we shifted the receiver by another 5 meters. Right, now it is 10. So, 0, 5, 10. So, now we have 3 subsurface configurations obtained at 3 locations which are separated by a distance of 5 meters. So, this is how, using electromagnetic method, quickly we are able to derive the resistivities of the layer below the surface. Since we have the details obtained at 3 locations below the surface, right. So, we have below, this is the ground surface, we have information here, here, here. At 3 locations we know the variation in the subsurface resistivities. Then we can also interpret the layers by simple interpolation and arrive at the subsurface model of the terrain. Right. So, what we see here is the subsurface cross section based on the variation in either conductivity or resistivity. Right. They are inversely related. First, let us have a look into resistivity. So, resistivity of this layer seems to be little bit higher, whereas here it is little less, and I told you usually 3 times will be the depth of penetration. So, up to 60 to 70 meters we could get, right. Here at beyond 50 meters rocks are appearing to be little bit fractured, right, whereas very close to the surface also there seems to be a fractured zone, right, at a depth of about 25 to 30 meters. So, this is how we are able to get the subsurface section, right. And since we have done sounding at 3 locations, whatever I showed you on the previous slide, same thing has been written in the form of a table here. So, this is how we have to include the results in the report which we are going to generate. That means we did at 3 locations, right. At 3 locations we could get 4 layers until the depth of penetration of which was about 70 meters. This is how the resistivity varied at 3 soundings, right, and corresponding thicknesses of layers are also indicated here, right. Though they are at a distance of only about 5 meters, there is some marginal difference in the values of resistivity. Then all these 3 soundings were interpolated, right. This is 0, 5, 10, right. They are interpolated and then we could get the subsurface model of the terrain. So, today we have understood how electromagnetic survey is carried out in the field and how we could get the data directly from the EM meter. After obtaining the data can be also processed to get the inverse 1D model. After having the 1D model at 3 locations, we can also perform what is known as inverse subsurface cross section or image, as you can see in this diagram, can be obtained using electromagnetic method. I am sure you would have had a feel of carrying out transient electromagnetic survey. Thank you so much.